thanks the organizer for being here. It's, I think, my fourth time. I think it's a beautiful place and beautiful workshop, and I hope all enjoy it as I do. And I have to thank Tim because, I don't know, maybe not, because essentially he gave my talk. The idea is from Bell inequalities to many word interpretation. And the final kind of point of Tim is that we have to live with this spooky action at a distance. And I think this is a very good reason to reject this idea, to look for something, and the only way without spooky action at a distance is the many words. And this is kind of was the main issue which I wanted to say. But and essentially I had the same arguments, and the first, I thought 40% of my talk was really doing exactly what you did. But since I do it somewhat a little different with some pictures, with some equations, and I saw that not all students ask questions. So maybe if the same story will be repeated twice in different angles, maybe more audience will be kind of more active. So I think there is, and there are some nuances which are not exactly as Tim. Maybe I'm an example of these mistakes, at least partly, which you were talking about, because I do think that I will, in the end, I agree with your main point, but I think randomness is very important. We'll discuss it. I'll discuss it. Now, the second half, it's really not related to Bell's theorem, but it is related to Bell, because Bell gave me inspiration to think about something which I think very exciting. My most recent result, which I found exciting, and was started from, I think, the beginning was really Bell in an unrelated work. And this work was related very much to Booleans, and I knew always the Boolean mechanics is very popular in Sesto, so I think it's the right place. I also will end with giving a quiz, which requires pretty good knowledge of Boolean mechanics. And there is a prize, a T-shirt pretty much similar to that one, but somewhat different, with a partial solution of a quiz. So let's go. To talk about Bell inequality, I completely agree with Tim. You have to start with EPR. You cannot jump to Bell. The first is the EPR argument. So I will try to present here the EPR argument. I think it's pretty rigorous, including the mathematics, and in the way which you don't have to be a trained physicist to understand it. So if there are some philosophy students, I think this is helpful. So it's not very much different. In fact, pretty much identical to what you did. So I think it will be easier. So let's start with the PR paper. The conclusion was that while we have thus shown that the wave function does not provide a complete description of the physical reality, we left open the question of whether or not such a description exists. We believe, however, that such a theory is possible. And the Bell theory, really, I think, putting no to this final sentence. I want to start in the PR argument even before this. Let's start that you don't know quantum mechanics. The first thing about quantum mechanics is the superposition principle. Let's say you have a particle in a particular place. It's described by a state. You can put some frame of reference and call it the state x1. And it might be in some different place, which you call state x2. Superposition principle tell us, quantum mechanics tell us, that invariably there will be many other states which are superposition of these two states. If there is one, there is another one. There is any superposition alpha x1 plus beta x2. Here it's alpha 1 x1 and alpha 2 x2 also exists. Operational meaning, it's somewhat not very clear, but at least in this meaning, if you try to look for a particle in x1, you will find it with probability alpha 1 square and alpha 2 square in the second place. So we have these quantum states. I discussed about one. Let's put them in position -1 and +1. So we have a state -1, we have a state +1. We have a state as a superposition, let's say equal superposition. Now, in addition to equal superposition, there is another one with equal superposition, but with different phase. What I said before, that operational meaning, it's to find with probability according to alpha, and here the alpha is 1 over square root of 2. So the two states look similar. They have the same predictions. Probability half to find in 1 and probability half to find in -1. But these states are really different. They are different. They have this one with plus and one with minus. And this difference can be seen operationally. What we can do to see this difference is the following. Take this state and arrange send them, arrange some forces, send these two particles through a beam splitter. Not particles, really part of the state, superposition, but we arrange physical devices which will send, if they exist there, they will be sent, like this. Now, if it's a plus state, when it'll come to a beam splitter, it will go to one direction. If it will be a minus state, it will go to another direction. These two states are really completely different. Quantum mechanics are orthogonal, and the difference can be measured where they go if you send them to a beam splitter. Let's put another axis. Let's call it y-axis, although it's parallel to x, but it's after the beam splitter. Let's call it y variable. So these states correspond to a definite y variable. The +1 will go y equal 1, and the left one is y equal -1. So the same superposition, we can give another name. It has another variable. It might have x variable and y variable. And the superposition of two values of x correspond to a definite value of y. Now, the x variable, if we take a definite x value and send it through a beam splitter, it will not come to a particular y. It will split in two places. So it will be a superposition of y's. If we'll take another x, it will also go to a superposition of y's with the same absolute value of amplitude, but with different sign. So we have this x equal 1. Of course, it cannot be the same superposition because there are different states. So now we have a list of quantum states. X and y are variable. This is a way to write them using the x variable. This is a way to write a y variable. And now we see that these four states, two of them, x is well defined, known, and y is not. And another one is y is defined, and x is not. So the property of quantum mechanics, the formalism, that x and y cannot be defined together. When x is defined, y is not known, and y is defined, x is not known. So this is really a property of quantum mechanics. So also, let's maybe say a little more about this measurement. The probability to find it in one was alpha 1 square. When we make this measurement, the collapse happened, something which is strange. We started with superposition here and there. We make a measurement. How we can make a measurement? We can send a beam of light. These are photons going here. And if they reflected, then we know that there will be no reflection whatsoever on other parts. From now on, the particle is here. It might be that we send the photons, they go and not scattered at all. In this case, we'll say, oh, we found the particle in another place. Before, it was in superposition, but now it will not be in x1, it will be only in x2. In the moment when the photons come to the particle, there is this collapse. And this collapse is really random. Quantum mechanics says there is a probability of something to be found. It's a random event. And here I put Einstein, God does not play dice, and I think Tim is correct. Probably Einstein wasn't so upset about this randomness. He was upset that really what I'm doing here changes something there. The non-locality was much more important for Einstein. But I think also the randomness, he didn't like it. I just finished a paper, Quantum Mechanics and Determinism. And I wanted to find support for the philosophical idea that the scientific theory should be deterministic. And I realized that it's very difficult. So Einstein looked like the only serious support. I didn't want it to say no, he was really talking about non-locality. So I want at least him. It seems that quantum mechanics, and if I would go like 120 years ago, and even after Newton and Laplace, everyone said physics, of course, deterministic. This is how it should be. This is how science is. But quantum mechanics spoiled this idea. And today, everyone believes that determinism is not really necessary. OK, so I want to keep Einstein with me.
That ball is a micro or a macro object?
You know, I believe in many word interpretation. For me, there is no difference. Okay. Everything is quantum mechanical. But here, I consider it as a micro object. It's a proposition, something I can make an experiment. I can put a neutron there or electron in a superposition. Yeah, yeah. But such that there will be enough scattering of my. Yes. Be careful about the coherence and other stuff. Yeah. So consider it micro. So it's easy to make it not decoherent. This was your problem?
No, it's macro.
Micro. It's better. Yeah.
Okay, even if it's small, if we want to do the experiment, we should send photons to it.
Yeah, there's many photons scattered. Many photons, I have an atom. This may be an atom. This is a realistic thing. Photon do scatter from atom pretty well. So, what?
There is no randomness in the result of this scattering, because if we want to do the measurement on Y.
I assume Gedanken situation, not so easily to done, but possible to done, that if the particle is there, the photons always will be scattered. This is, yeah, this is the idea. This is, OK. So now let's go to EPR. Quantum mechanics allows also entangled states, which are not product state. This is an entangled state. We have two particles. One particle in a superposition here, and another particle in a superposition here. And they are connected to each other because this is how you write this quantum state. And the operational meaning is that if you'll find particle A in -1, B also will be in -1, always. If you send the photons here and they will be reflected from here, the same will happen always in another one. And if you send photons, but it was not found in -1, so from now on it will be 1, the same will happen there, always. I can, the simulation, I can maybe repeat it. I send again, always happens this thing. If this happens always, then we really don't need to put photons both here and here to know what will be the outcome here. It's enough just to do it on one side. We can send photons here, and from now on we know this will collapse too. There will be no -1 on B, it will be only 1 on B. So we can make a measurement in A, action in A, and to know XB. There is a probability half to find also here, because amplitude is 1 or square root 2, probability half to find -1 and +1 in B. But we can measure it in A, not in B. This is what EPR realized. Now, this is about X measurement. If we'll take this wave function, the EPR state, and we rewrite it in Y variables. Just, you remember what I wrote before. 1, it's Y plus -1. I can have to replace the X equal 1 by 1 Y plus. X will here with a minus. You just write it, do a little algebra, and you get that it has the same shape. In Y, it looks like in X. So it's also kind of an EPR state This is EPR state. This is a property. Whatever basis you use, it looks the same. So in Y, it looks the same. And if you, the same story, if you measure, find 1 in A, it will be 1 in B. And the same about -1. If you send, you take, to measure Y, you have to use your beam splitter first, and then you send your photons. And they always agree. It means that you don't have to send photons both here and here. It's enough to send photons just in A. You send them in A, and you know what's happening in B. Now you send both cases, but it's enough to send just here. You send just here, and you know the outcome in B. So you can measure both X and Y by operation here. So now we are ready for EPR argument. We prepare this EPR state. We know that XB and YB is possible to measure in A. Einstein, after relativity theory, or maybe even before, didn't believe in any action at a distance. So if we do something here, we cannot change anything there. Therefore, this XB and YB exist even before the measurement. Relativity theory, no action at a distance, measurement in A causes no change in B. X and B can be measured without disturbance. Therefore, XB, YB exist. Before we say quantum formalism does not allow to have X and B together. Quantum theory, X and Y in B, also in A, are not defined together. However, they must exist because we can measure them in this using the EPR state and measurement in A. Therefore, quantum theory is incomplete.
Tim pointed out this morning, however,
Yes.
quantum theory wave function description would have been incomplete even if only XB existed.
I think you're right, and I believe Einstein even has a paper on this before. I think he has some paper in which he was very upset that you have a wave function both here and here, essentially what I presented in the beginning. You look in one place, and it immediately collapses. It's not there. What I emphasized that the randomness was bad. He really emphasized that non-locality was bad. The wave function before was both here and there. You make measurement here, and something there changes. Before it was half a wave function. Now there is nothing. Oh, there is a fall. It's different. So I think he had this argument before, but it looks like even this one was not accepted immediately. People, in the beginning, people didn't pay attention. Not on the first paper of Einstein, and then on this one. There were many years till it started. In fact, until Bell, I think it wasn't really a big story. Okay.
But Lev, I insist that those objects must be macro objects. Because if you have an atom and you send 5 photons on it, quantum mechanics can perfectly describe the state, and there is no reduction of the wave packet.
But
So either you postulate the reduction of
no, the reduction is
at the microscopic level.
No. When I make a measurement, what I draw, maybe let's see how back I have to go. Like here, let's put some scattering. You see, I send these photons, but these photons are absorbed by me. So there is I don't talk now really about reduction. The idea is there are many photons. Maybe the reduction happened when the macroscopic observer. From my point of view also, to say that you say reduction, I say splitting to different words, which I don't think it's a physical process, and it's not important for me where to put the boundary. But clearly, I will say that only when something macroscopic moves or changes its state, then I say it's a change in different word, or there is a collapse, or whatever. So when there are many photons, these photons may be absorbed by some. Okay. Let me EPR argument. Okay. So why will have again? Here I repeated the conclusion of EPR. So they still can. They believe that they say it's incomplete, but they could believe that it's possible. If I look on this example and what I did until now, this EPR state, and I look on x and y variable. This is in x basis, y basis, and here I change. I have one particle A in x basis, particle y in y basis. This tells me what will happen if I measure one in x and one in y. So in x basis, the product should be 1. You see, 1, 1, and minus 1, minus 1. Y should be also 1, product of y. 1, 1, minus 1, minus 1. Now, but if we look on the product of a different one, xa, yb, then this is a quantum state. It has a term 1, 1, and it has a term 1, minus 1. So the product might be, quantum mechanics will tell us both 1 and minus 1. So for this kind of outcomes, when we measure, we can easily construct hidden variables theory. It will be, let's say, 1, 1, 1, 1. No contradiction whatsoever with predictions of quantum mechanics. If we look just on x and y, we do not run into contradiction. We have to look for more variables. And this is what Bell did in '64. Now, one thing you was talking about the Bell proof itself. I find it a little difficult, so I will use another way. But anyway, this is a Bell's paper on Einstein-Podolsky-Rosen paradox. With this conclusion, which essentially said there is should be kind of spooky action of a distance, if you want to use kind of simple language. And he really considered these kind of things, and the proof may be not very complicated, but I find easier to think just about x and y. I already explained to you x and y, and this is enough to give you a proof that there should be action at a distance. However, for this, I need to consider 3 particles. So the one way is to consider more variables just for 2 particles. But the simple proof is 3 particles, which also Tim mentioned or described. And I will repeat the GHD story, the Grinberger-Hor-Zeilinger. I think Merman is important because until him, it was really 4. They had an example of 4 particles. So this is really the paper of GHD in '89. Merman transformed it to 3, and I don't know if I did any kind of variation or not, but I kind of called it a game, and this is how I understand it, maybe more simply, and this is how I present you the GHD result, and will show that there should be some spooky action at a distance. So this way, if you have a friend which know nothing about quantum mechanics and you want to impress them, I think this is the best way to do this. Just tell them the following puzzle. There are 3 friends. Here it's Young, Grinberger, Horn, and Zeilinger. And they kind of in separate rooms, so maybe far away, and you come to them and you ask, and there is a team who asks them questions. The questions are simple. In fact, there are only 2 kinds of questions, question X and question Y. No other questions. And the answers are also very simple. They can say 1 and minus 1. You ask X, oh, X equal 1. Oh, X equal minus 1 is the same about Y. Now, there are some conditions to win this game. If all of them ask X, somehow you make it the opposite, but I think this is a canonical form. If all ask X, the product should be minus 1. If only one of them asks x and two others y, the product should be +1. And only these four options, it will never happen that two of them will be asked x. Only all three, or just one. But all options, A, B, and C may be asked. This is all this. And to win, if they answer corresponding to this table, they win the game. So you ask your friends to do this, they start kind of work. It's high school exercise, how to arrange. And again, these guys sit together first. They can prepare a strategy. They can decide what they will answer on every question, because they know the game. They have to be prepared. And you ask how well they can do. And you'll see that you will work 5 minutes, 10 minutes, but more than 75% win you will not get. We'll see also why. But if they have quantum devices, which unfortunately today we're still not there to make this experiment to win this game, although there are tests that all this okay, but no fidelity and no detection efficiency for this. So they will have this GHZ state. You remember the EPR state was just 2 particles. Now we have GHZ state. We have 3 particles. And I want to use only x and y. Therefore, I have to use this notation. I have these 4 terms. Minus minus 1 for x. And again, this is just in x. Minus 1 plus plus. You see, if all of them ask x, it should be minus 1 the product. So this is OK. This is OK. And now I put minus in some other place, only in one place. So all these terms are OK. So this state is OK. If everyone is asked x, there will be either 3 minus 1 or only 1 minus 1. So they win in this case. Now, if I rewrite it in another basis, so this is OK. If I rewrite it in, for example, because now you can see it more clearly, minus 1, this is what it is. I can rewrite it in another basis, like using this x is y plus y, x minus 1, y minus 1. I rewrite and then do some algebra. It will be again 4 terms. Here I make the first one x and the 2 others y. And this other state is also fine. It's minus 1 for y and plus 1 here. In every state, here all pluses. And here there is 2 minuses, here, and again here. So in this case, if they measure x, the first one asked x, and 2 others asked y, we know that with this state, it will be OK. Their strategy is simple. They have these particles, and every time they ask x and y, x, they just look where is the particle, and y, they put a beam splitter, put it through, and then look where is the particle. They measure y. Now, if this works for this will work for all of them, because there is a symmetry, in fact, in this state. So if all other cases also will be fine. So quantum mechanics allows to win this game. If they would have these quantum devices, and every time they ask questions, they just will make this quantum measurement, they will win the game. Here, just the classical attempt. One try to arrange something classicalist. So let's say he will choose minus 1 here. For this one, if xa should answer minus 1, it should be always minus 1. So if there are, never mind what others asked. So it again minus 1. I choose here 1 minus 1. I can fulfill the third one again because it's 1. He is not asked this. So this is in fact, I can choose whatever I want because y was not asked. So I can make, of course, I can fulfill because I can arrange this. This should correspond to this, and this correspond to this. The fourth one is forced on me because I already know what should be, and it's come out wrong. The way to prove it, maybe Tim's proof even easier, but here it's very simple algebraic proof, which is essentially equivalent to this. There is no way to fulfill this equation, all of them. because if you make a product on the left side, you will get squares. And you have a product on the right side, it's -1. So it's impossible that these quantum particles know in advance what they will do. No way. Because if they know in advance what they will do, they will never be right for any question whatsoever. They, 1/4 of the cases, they will be wrong. So the values can be found by a measurement far away. We can make a measurement here, and then the third one is known, because it should fulfill these equations. But there are no values which correspond to these outcomes. So this is a proof that quantum theory cannot be completed. It cannot be completed. We have this, we know the experiment confirmed that these are quantum outcomes. They cannot know it locally what to do. So before the experiment, they should not know. You come to the experiment, they should decide what to do. So I think that the language, it's kind of contradiction. Or if you want, EPR tell us, if you want complete quantum mechanics, we have contradiction. If we add Bell, we have contradiction with any local theory. So the first lesson which I like to conclude, that God plays dice, because this experiment don't know, the particle don't know what to say before they do. They cannot know to fulfill all of these equations. The second question is that if we measure here, the third one immediately have to know. So it looks like there is an action at a distance. I agree with Tim that in the moment we'll say, oh, there is an action at a distance. If there is an action at a distance, then the playing dice doesn't work. I got that it should be randomness because I assume that there is locality. Then I say, okay, let's add randomness. And this was not enough. I add randomness, it's not enough. I should say, oh, there is non-locality. Now, if I assume non-locality, I don't need randomness. As Bohm showed in 52, we have deterministic local theory, non-local theory, which correspond to EPR experiment. So it's really, there is no proof of determinism. Only if you say, oh, it should be local, now I prove that it's random. But then it's a bad proof, because if you say, oh, the random is not enough. So from my point of view, it is a paradox. I really, I believe that all physics is local. I believe that things here, I'm not supposed to move, so I can maybe move. I can move this only because I touch it. And I don't believe in any spooky or not spooky action at a distance. And so this is why I believe in many-word interpretation, because there I think no action of the distance of any kind. And now even more believe so, because I still felt bad. My teacher Aronov had this Aronov-Bohm effect, which my belief in many-word doesn't help me to resolve it. It's kind of, it's not action at a distance, but it's kind of, it tells us that there is no local explanation with local fields. I believe that all explanations are like this. Particles move around, they create fields. These fields move other particles. This is physics for me. And Aronov-Bohm was not like this. I have a paper which published a year and a half ago, in which if we consider everything quantum, also Aronov-Bohm effect, it's also like this. So I can believe that all physics is completely local. The only influence is through local fields.
That's all fine and good, Lev. But the fact that you don't like it doesn't make it a paradox.
Paradox are all kind of. I have in Tel Aviv. I have a course on paradoxes in quantum mechanics. So if there will be if we will find a paradox in physics, this is the most precious thing, it means that we'll find a new physical theory. This is how quantum mechanics come, whatever. Today, I don't think we have paradoxes, and so in the end, it's paradox under certain premises, which. But since physics is so successful, if I can have this simple explanation, I want to be with it. I don't want any complication of it. OK, how to resolve the paradox? Bohr said, all results I explained well. Don't talk about what happens between measurements, and you're OK. But I think it's not very helpful, because when you think about physical system in between measurement, you can find more things. Like this interaction-free measurement, without thinking what happened in between measurement, I think we would never get to. So I don't think it's consistent. I don't think it is fruitful. Collapse theory, there is an immediate action at a distance. If you have this kind of EPR situation, you measure, you do something here, something immediately changes there. For me, cannot be true. If I cannot believe in this theory, I should, like, if this, I cannot now believe that the physics is explain all nature. This doesn't look like.
Just a second, you can't believe that there is book action at a distance, but you can believe in infinite universes.
I will wait. Wait. OK. So measurement in A changes things in B. This I don't want to believe it. Now there are many parallel worlds. This I do believe, the many worlds. Look on this example, how at least no problem here. When I send photons here, I both get, they both reflected and go through. There is a splitting. There is this through and this through. And nothing whatsoever happens on the other side. Before it was EPR state, it was correlated to this particle, to A and B. Now it's correlated also to photons. Very understandably, because there was local interaction between photon and this particle, which was correlated to another one. So no miracles. It was correlation between two distant, they were together once. Now there is a correlation. And now you do something with this one. Now this one is correlated also to some other, to photons and to me, if I measure it. But the meaning of it is that I will see two outcomes. I will see the particles there, if it's I see these photons, and I will see the particles is not there if I see the detectors of photons there. I will split into a measurement in A split the world into two worlds, but the physical universe doesn't. In physical universe, nothing changed in B. No action at a distance whatsoever. So, yes.
One question.
Yes.
Does your operation there split the world into two worlds even when you have a superposition of -1 and +1 with different weights?
Yeah, sure.
Okay.
And God does not play dice. I really like that science is omnipotent in the sense it can explain everything. I don't want science will tell me, OK, for this experiment you come. Science gives me only some probabilities. It doesn't tell me if it goes left and right. Even I know everything about the universe. I think the theory which can tell me that what will happen completely is stronger and better than the one which doesn't. So the many words interpretation, this is kind of a picture. If you go to my homepage, there is a word splitter. You can split it for $4. If you have iPhone, you can buy for $2 the word as application. And then you can, every time you want different cakes too many cakes, it's not good. You can eat one cake in one word, another cake in another word. Sometimes when I give talks about many words interpretation, usually I try to connect to my word splitter and say that I start my talk from here if it's tell me left and right, and then two of me walking here. And it's kind of an experiment that I don't bump in another one. There is no problem. Like if you have an electron as a proposition, it can cross each other, no scattering. No scattering with electrons. When the electron is a proposition, the branches don't scatter on each other. And I don't scatter with other me walking here. Maybe just 2 or 3 slides about many words, because this wasn't really, I didn't plan to. It's a big issue. I don't know how long I need to explain many words. The many words consists of 2 parts. There is this physical part, wave function, evolving according to the Schrödinger equation. And the second one, it's a connection of this big wave function to my experience. There is a mathematical, physical part. This should be exact. Connection to experience, you can play with it. It's vague, like it's for us. It's not for ontology. Ontology, it's only the wave function. All is psi. There is a single psi, single physical universe, only one. This is a many word interpretation. There is only one universe, one physical universe with a big wave function. This big wave function corresponds to many experiences. Essentially, every different experience is a different world. There are all kinds of alternative definitions. I like that if a macroscopic object is in 2 different, macroscopically different states, these are 2 different worlds. Electron, quantum particle in 2 different worlds, it's still the same world. Now it's vague. What's macroscopic, what's microscopic? And it is vague. The word is our concept to explain how there is a connection between real ontology, which is just a wave function, to our experience. And the word is an important concept, but it's our concept for explanation, not for ontology. It doesn't move particles differently. It doesn't move anything differently. When there is collapse, is not a physical process. Not collapse, word splitting, what corresponds to collapse. Word splitting is not a physical process. It's just we described there is it was one story. Now there are 2 different stories which you can describe. Something of this kind. This is simple. If you send a single particle to a beam splitter, there are 2 detectors, and you decide if you see A, you move to right, and see B, you see to the left. From now on, you move. From my point of view, I'm a wave function, so I will move to these 2 places. This is what will happen if I'll make a connection to my not exactly, similar experiment happened in the basement of Tel Aviv University. It's timing, not really position. We have a single photon detector which look when exactly it's detected. So I think my main contribution to the many words is really understanding how you can understand the illusion of probability, how that's its self-location uncertainty inside in which world you are. And when I wrote the first version of this paper, I did send it to John Bell. I was trying to find this email. I'm not sure it's lost. But I think I remember it pretty well. It's how I remember it. I was pretty upset to get this. This is what he wrote to me. I was not persuaded by your paper, but I understand that this should not bother you. Surely in some parallel world, I accept your thesis. And in this world, and if in this world I like the paper, surely in the parallel world I do not. So what is the point of the many words?
Very practical.
I don't think so. I don't know if my feeling is that he never understood properly the many word interpretation, because this doesn't. All possible outcomes of quantum experiment happened. Not all possible words happening, like in David Lewis or something like this. So this paper, in fact, not just John Bell didn't understand. I think Putnam had even worse reaction. Dave Albert, who taught me many words, didn't like it. And referees didn't like it for 3 or 4 or 5 journals, I don't remember. It took me like 9 years to publish it. Although some editors later said that they believed it was a mistake not to publish it. But okay. So this other story, I will try to be very fast. Inspired by Bell paper, which in fact I didn't know, only a posteriori, is that if you take a Mach-Zehnder interferometer, in fact, in one of the papers, he said, and you look on Bowman particles, that Bowman particles behave strangely. You take Mach-Zehnder interferometer, take out the beam splitter, so there is nothing here. But the calculation shows that the trajectory should be like this. And this is kind of strange. Now it became more strange after the paper by Engler and company, who really gave the name these surrealistic trajectories. And so this means the following. If you put this experiment, Mach-Zehnder interferometer, in a bubble chamber, and here are some if you put this many special detectors there. But these detectors should be of special kind. In fact, usually you will say it's a good kind. But they're kind of slow. First they change their wave function, and only later they kind of expand. What I call non-Bohmian position detectors. Here, for example, if you have a wave, the measuring device is a particle inside the ring. When it detects the other particle, it starts rotating, change the angular momentum, but it remains in the same place. Now, from Bohmian point of view, in a sense, something happens. The Bohmian particle inside starts moving. But it's not enough to this is not really a Bohmian measurement. It's not like if you have a pointer, the particle goes here, it goes like this. In fact, I was pretty impressed by this paper. I think I was probably one of the first to see it. Aronov got it for referee. It was on his table. He gave it to me. And I read it. I think it should be garbage. It cannot be true because Bohmian is fine. And I read it several times and realized it's true. That sometimes you have to be careful. Not all Bohmian detectors are fine. And here there is a big, recently I wrote a big paper to say which position detectors are good position detectors for Bohm and which are not. How to classify them. Some of the Bohmian detectors are not do the job. They don't really find Bohmian particles. You see, detectors that say this trajectory, but the Bohmian trajectory is really different. I want to, there is probably I can extend a little because the question was also during the talk, but still, I want to get to the top, to the final point. And the final point of this work, which I was pretty excited about the past of the quantum particle. There are several works, and there are comments on comments, and whatever, there are more. And there is it's my first experimental work. The question is the following. I want to talk about the past of the quantum particle, really to be against Bohr. We started with particle here. We ended here. Let's look on this without beam splitter. I want to ask where was the particle in between. And there are all kinds of options. Von Neumann say it was a wave up till here until it collapsed here. Bohm will say it was like this. Wheeler will say, OK, it couldn't come this way. There is no beam splitter here. So this was a trajectory of a particle. So this kind of what we have options to say. And there are criteria. One can say, I can imagine non-demolition measurement trying to find where was really the particle. Then I will see that Wheeler is right. I like the criteria about weak trace. Because everything, even this laser, it's really weak. You hardly see it even there. Whatever, I believe it leaves some trace. When there are some neutrinos there, they change their wave function slightly by 10 to the minus 100. But the wave function changed. They don't go to orthogonal state. But if I put here some photon, something changed. Even this is really a lot of things changed. But photon usually, since they make interference, they don't do strong coupling, but they do some coupling. There is no zero coupling. So there is a weak trace. If you will make many measurements, you can find everything started here, ended here. In the end, you'll see that the air here was heated and here not. But only for the particle, only for the cases where this, when you get a click. The other thing, if the particle, I think pretty much the particle was not here. So if I try to push it here, nothing will happen. If I put a piece of glass which shifts the particle here, I do not expect that the photon which the particle was found here will be shifted. So from this point of view, this is a trajectory. If I put a piece of glass here, it will be shifted. Put it here, it will not be shifted. So maybe this is the right thing. But I really wanted to come to laboratory and to make an experiment. OK, this is first. So we have this Wheeler, just repeat the Wheeler story because it's important. We take this out, and this is wave, you see. Now you see the wave. And then we get the click, and Wheeler will say that it was here because it couldn't come the other way. This is a Wheeler story. The Wheeler story, it's important because I want to make an argument about it. It also worked in this case. So one case was this Wheeler delay choice experiment takes the beam splitter out. But he also instead took a mirror out. If you take a mirror out and you get a click here, he knows the trajectory. It couldn't come any other way, only by this line. You can change it a little, even a little more. Let's complicate it. Put this instead of to add here interferometer, but tune it very well that everything go out here. So it cannot really start from here and end up here. So in this case, I think it's very persuasive idea that the photon, if we want to talk about where it was in between, should be here. It could be any other way. It couldn't come from here to here. I talk about the photons which we found here and started here. Now, textbook. 2 minutes as I see it. But there were many questions, so let's put some of it in. Yeah. Okay, textbook says this story. We have a wave function and it disappears when we get click. But before disappearance, it was all over. So this is the story of the standard wave function. Different picture. So this is a picture of textbook of von Neumann. And this is Wheeler. And I wanted to find an experiment to find out who is right. How I make an experiment. I wiggle one of the mirrors with particular frequency. Here I put special detector, which is quad cell detector. It has, in fact, 2 detectors. One here, in fact, not quad, one here and one here. And I measure the difference in the current. When it's go up, more current here, more current here. So I have this signal. And I wiggle and I make a Fourier analysis, power spectrum, which frequencies I have. And I wiggle this with some frequency, up and down. And of course, I see it here. Now, I do it in I also put some other frequency here. And this is a Mach-Zehnder interferometer with beam splitter. And I saw both this one and this one. So I can say maybe some photon, so every photon was both here and here. Now, I made this experiment, which I want to discuss. Took this out. I don't see this frequency disappeared. So now I can say who is better, von Neumann or Wheeler. Wheeler tells me that this is the trajectory. This is wiggling, but the frequency which I see only B. Von Neumann says the photon was everywhere. And in the end, but I see only B, not A. So I say Wheeler is right, textbooks are wrong. It's too strong. You cannot use the idea of past of the particle with a textbook. You have to make it much more, you have to talk about entanglement, whatever. You can explain it, but in difficult terms. If you want to use the concept of past of the particle, Wheeler is fine. If Wheeler is fine, let's test that he's fine everywhere. Here we found it's fine. Wheeler says it could be everywhere here. So A and B, and we see frequency A and frequency B. Photons, Wheeler is right. If we cut some of them, it couldn't come through A, no frequency A. Fine. These are real results. We cut another one, no one. Now I wanted to play more, my first experiment. So I put inside one interferometer, and there is a big interferometer, and I tuned as I could in this way. And I split these beams, 1/3 here, 2/3 here, 1/3, 1/3. And all mirrors were wiggling with different frequencies because I wanted to know where were the photons. And I got a picture which is understandable. A, B, C, E, and F. And E, F bigger because bigger part of the beam is there, so the effect is bigger. And the reason why I say I was excited, there is no reason to be excited until now. Wheeler is right, is this experiment. So it's the same like previous one. With only change, I didn't change anything. I only shifted a little with this one, so to make essentially put pi phase here. So now there is a destructive interference here, and everything go out. And I didn't show what I got. If no one had this story before, please tell me what you expect.
I already know.
You see, if Wheeler should, the only way to come is through C. So it should be C. But if I ask, so then it cannot be just C or cannot. So what any guess just? Okay. So this is what we saw. Oh, it was a guess. But I see you know too. What? What? Yeah. T-shirt is somewhat slightly different. It's coming. So you see A, B, and C, and no F and no E. And this is strange, because you see Wheeler say it should be just C, and I also get A and B. How this frequency can come to here? Why wiggling of the photon here do something there? It's really strange. And if there is one, if the photons do come from here, they only can come through F. But there is no F, and there is no E. Maybe textbook says there should be no F but E, but the textbooks are wrong too. So if these are wrong, textbooks are wrong, what is right? 3 slides on what is right, the two-state vector formalism, which gives the explanation of it. There is one wave function, there is another wave function, and in the middle you have to take into account both of them. In this case, this is a one wave function, the simple case. This is another wave function. Now two together. You see, here there are two together, so the particle was here and we see it. Now the surprising case. This is a surprising case. Forward one, backward one. Two together. You see here there are two together. Here, two together. There is one. One is not enough. You need two state vectors, one going forward and one backward, to say that the particle was there. Because only then it can, if I can do something, I can know about it. So the particle was here. And this is exactly the signal we got. It looks like a paradox. People talk about photon trajectory, maybe many trajectories. This shows the weak trace is really here, not here, and not here, against the idea that photons move by all kinds of trajectories. For me, it's a paradoxical situation. And how to go out of this paradox? Come back to many words. This paradoxical situation, it's just for me in my world. There is no such thing in the physical universe for God. For God, there is a click here, and click here, all these three things. If we make a backward evolving function of all experiments together, like here, then we'll get a photon from here and photon from here. They will destructively interfere here. They will not go there. This is the story of the physical universe altogether. It's not paradoxical. From God's point of view, we have only one wave function, only psi and psi going backward. So the many world wave function is forward and backward, the same wave function. It's only for us in a particular world that second one is as important as the forward one. When we made the post-selection in a world, we made a post-selection. Two of them go together. The weak trace continues if you consider the whole universe. A T-shirt. A T-shirt for person who solves best the quiz. It's not exactly quiz because I think you can give it until the last lecture of this workshop. But again, if somebody, you write the time when you give it to me, and if somebody do it before and as good as, the first is the best one. The second one, if there are several best ones, the one which did it before, there is only one T-shirt, not exactly like this, with solution of this puzzle. The puzzle is the following. It's kind of the things which Bell did for Wheeler without a beam splitter, I ask you to do for my interferometer. So you start with my interferometer, and I don't ask about this one when it's tuned in this way. Now you tune it as I want, that 0 is going here. There are clicks possible here, here, and here. And I like that this exactly crosses. So here the Bowmans can really go from one to another one if they should. And you should give me all possible trajectories for this case, and this case. There are here the lists. There's 6 cases, 1, 2, 3, and I don't know. Then it might be less, or even more. I don't believe there is more. Not more than 4 for any kind of cases. All possible trajectories for this, and this. And there are 3 more. Now you put all this in this special bubble chamber. This special bubble chamber measures in non-Bowman way the trajectory. There is a trace, but non-Bowman trace. These things measure where the same experiment like here, in this with Bowman, with measurement Ala and Glaert, Scala, and Oton. Now tell me if there is any difference. Bell said there is no difference. And Glaert said between Bell case and Glaert case, no difference. Maybe here there is a difference. So this is A. This is how it is. This is 3 questions with this tuning, and 3 questions when you put it in. And here are my conclusions. Only on the first part, I believe that Bell's theorem tells us that the nature is apparently random and it has some kind of action at distance. In my view, these are unacceptable properties. And the many word removes randomness and action at distance from physics, explaining why we have an illusion of randomness in Bell non-locality. Thank you.